PACEbench, a framework for evaluating practical AI cyber-exploitation capabilities. The paper investigates a core question. Can current AI models autonomously find and exploit vulnerabilities in realistic computer networks, not just in simplified test cases? To do this, it introduces a new evaluation framework. It's designed to measure these capabilities based on 3 principles, using real-world vulnerabilities, simulating complex networks, and including active cyber defenses. The headline result is that the highest score achieved by any tested AI model on this new benchmark was 0.241 out of a possible 1.0. This score is a weighted success rate across multiple exploitation tasks. That low score leads to the paper's primary conclusion. Based on this evidence, current AI models do not appear to pose a generalized autonomous threat for offensive cyber operations. Before we get into the new benchmark, how were these capabilities typically measured before, and what were the shortcomings of that approach? Prior evaluations often used capture the flag, or CTF, competitions. These are simplified scenarios that usually focus on a single target that is already known to be vulnerable. This is different from real-world attacks, which involve navigating complex networks with non-vulnerable systems and active differences. This creates 3 main gaps. First, prior methods operate with a presumption of guilt. The AI agent is told which machine to target. Second, they lack environmental complexity, like benign hosts that act as distractors. Third, the AI agents were often custom-built for these specific tasks, not for general-purpose exploitation. So how was this new framework designed to address those specific gaps? It's built on 3 design principles. First, it uses real-world common vulnerabilities and exposures, or CVEs, with known difficulty levels. Second, it simulates multi-host networks, which forces the AI to identify the correct target. Third, it includes active countermeasures, like web application firewalls. The benchmark itself consists of 4 scenarios with increasing difficulty. Scenario A is a single vulnerability on one host. Scenario B adds benign hosts to the network. C requires chaining multiple exploits for lateral movement. And Scenario D tests the AI's ability to bypass a web application firewall. To conduct the tests, a custom agent framework called PACEagent was developed. It's designed to emulate a human penetration tester's workflow by separating the process into 3 phases: reconnaissance, analysis, and exploitation. And which AI models were evaluated with this framework? 7 large language models were tested. 4 were proprietary closed-source models, including Claude 3.7 Sonnet and GPT-5 Mini. 3 were open-source models, including 2 from the DeepSeek family. Here are the final scores. The proprietary model Claude 3.7 Sonnet achieved the highest score of 0.241. A clear performance gap exists between the proprietary and open-source models. One model, DeepSeek R1, scored 0.000, failing to complete any exploitation. A key finding was that model performance degraded as the environment became more complex. Models that could exploit a vulnerability in the simple scenario A often failed when they first had to identify the correct target in the multi-host scenarios. This was most evident in the defended scenario. When a web application firewall was present, the score for every tested model was 0.000. No agent was able to bypass this defense. How did the custom agent, PACEagent, compare to other existing agent frameworks? It was compared to the CAI framework. When using the same underlying AI model, PACEagent achieved a 65.2% higher score. This improved performance had a cost. PACEagent used 28% more tokens on average, showing a trade-off between performance and computational expense. Stepping back, what are the broader implications and what limitations did the paper identify in its own work? It states 3 main limitations. First, the most advanced premium models were not tested due to cost. Second, the benchmark currently focuses only on web application vulnerabilities. And third, the test set includes a total of 32 unique vulnerabilities. The paper also looks at future risk, stating AI-driven cyber exploitation presents a significant dual-use dilemma. Right. It argues that as AI capabilities improve, research should shift towards constructive, defensive applications. For example, using AI to help find and fix vulnerabilities, not just to exploit them. So to conclude, what are the primary actionable takeaways here? There are 5. First, evaluate AI capabilities using realistic benchmarks, not simplified ones. Second, measure performance against a range of vulnerability difficulties. Third, test agents in complex, multi-host environments that include distractors. Fourth, assess AI performance against active defenses. And fifth, pivot research toward defensive and constructive applications.